Close.
So close. Cool. Yes, right, there you go. Hello, yes, my name's Owen. I'm a British-born, formerly London-based, now Reykjavik-based since 8 years, visual artist, software developer. And yeah, in terms of what the scene in Iceland is like, I think if we had one of these, it would be about 5 of us. But it is conveniently situated halfway between Europe and North America. So if you want to do the next one there, just saying. Right, so I'm going to give a talk called, depth scattering in TouchDesigner. It's basically particles coming out of depth maps, which I think for some of you will be a fairly familiar technique, but I'm just going to go through it from the very basics. I think the subtitle of this talk, especially considering what I think Richard was showing at the beginning, is This is Why Pops Exist. So I'm going to show you the hard way using compute shaders. And just a quick show of hands, who is playing with compute shaders? Okay, all right, that is, all right. So this might be a bit codey and a bit nerdy, but this is based on just a short article that I wrote. It's up on my website. I can share the link at the end, which has all the code that you can just grab and some example TouchDesigner files for you to just grab. So the effect, the end effect is something that looks a bit like this. So this is way too high resolution. There we go. Can I play that? Boop, boop. Oh, that's because that is an image. That is a video. There we go. That's better. So I have been playing around with this effect to make sort of various music videos and live visual work, and it is basically coming from the point of view that I am a very lazy 3D designer. I do not like modeling things in 3D. I like using things that are very basic. And then I get bored. I don't want to be sitting there fiddling in details. But with this one simple trick, you can make it look like, if I turn that off down here and switch this one on, computer, you can take a fairly uninspiring scene like this with some very simple models of grass and various things, and make it look, in my mind, a little bit more interesting like this. So if I open up the parameters of this guy, add the lighting color, we can add some... see, I turned up the scale on my screen so you guys could see the parameters, but I feel like it's now maybe a little bit too big, but that's fine, we can work with it. So what this is doing is rendering a very simple 3D scene just with some very simple lighting, and then taking the depth field and the color information from that render, and then using that to drive a particle system. And what I've really enjoyed about this is that it's super easy to art direct it. Like if you're spawning particles, quite often maybe you're saying like, okay, I'm going to spawn particles in a sort of somewhere within a random circle or somewhere within a random cube. But actually I want to spawn this onto the surface of a 3D model, and I don't have like a depth scan, or I have the 3D model, but I want to maybe use my existing 3D assets that I have, and I want to give it this kind of almost LiDAR kind of effect. So I'm going to go through how I've been doing that from sort of first principles, and then some twists at the end. So actually, what I was meant to do was set my timer so that I would stay on time, and I completely forgot to do that. So I'm going to go now. Okay, right. So the basic simple setup is. So if we scroll over to the side, so I'm going to start with a very, very, very simple 3D scene. So I just have 3 simple SOPs. I'm adding a color using the point SOP, and we're going to merge them together, and then we just have them coming into a geometry. This is all fairly familiar stuff. And then we render that using a very normal camera, and we have a very normal light going into a very normal render. The next bit afterwards is we're using the depth top. How familiar have people been using this a fair bit? Yeah, a few hands going up. So all this is doing is, like, normally the depth map is going to get discarded and used only during the render process to work out which pixel is ahead of which other pixel when it's rendering the whole image. But we can extract this depth map and use it to basically fire particles randomly out into the scene, and wherever they hit this depth map is where they're going to be spawned. And we're going to do this using compute shaders. So this is where it all gets very, very code heavy, and I apologize. And also, this is why POPs exist. We have a GLSL multi, which is an operator that allows us to run like an arbitrary shader or compute shader on whatever textures are coming in. We have a noise because we want to scatter randomly, and we're going to use this as our starting point as to where we're going to fire our particles from. This is just to give a nice kind of like even spread of particles throughout the scene. And then in the second input, we are taking the depth map from the render that we just used, and then we have the compute shader. So I won't go through this in too much detail because it's very code heavy. But we are basically, first of all, compute shaders, for those of you who haven't worked with it but have worked with fragment and vertex shaders, they allow a lot more flexibility into where you can write and when you can write and the way in which you can write data. It's a little bit more like writing pure C on the GPU, and things aren't sort of constrained as much into this graphical kind of mindset. You're dealing with pure data. At least that's my kind of interpretation of it. So what we're doing here, we're grabbing a random, for each, it's stepping through each pixel of the input texture, and we're grabbing a UV from the noise, and then we're going to use that to look up into the depth texture. And I have a little diagram of what that looks like here. So the noise texture is, say, that gives us a value, a red and a green value of 0.45 and 0.25. So we use that to like sample the depth texture at U 0.45 and V 0.25. And let's say that gives us a depth value of 0.2. From a different point of view, this is the camera that rendered that, and we're sampling this point on this ball. So what we can then do using matrix math is calculate if the camera saw this at 0.2 units in the depth map, we can reconstruct the world space position of where that particle was, and then use that to spawn a particle in world space again. And the end result is going to look, hopefully, something a little bit like this. So we get this kind of like scanned kind of LiDAR effect. And the wonderful thing, I should also say, the wonderful thing about meetups like this is that you all get to come up to me afterwards and say, actually, there's a much better way that you can do this. And I really welcome that because that's also part of this talk. So here comes the matrix math. First of all, we need to be adding, grabbing the inverse camera projection, which is a matrix. It's a series of numbers that describes how the camera turns a position of what it exists in the world in front of it, even into something that happens, something that exists on the screen. It's changing it into what we call screen space coordinates, which is, in this case, I think it's +1 to -1 in terms of the left and right, and the same with the up and down, and then also the near and the far plane of the camera. That last bit is very important, and we'll get onto that bit later. And what this is, all this compute shader stuff, which I won't go through in too much detail because I think it's more interesting to focus on the result, is sampling those things, performing the math, and of course dividing by W because, matrix math, weird, always divide by W. Don't know why, something to do with it existing on it anyway. And then storing that out as what looks like another random set of positions and values, which are actually the XY positions in world space for the particles that have been fired into the scene. One very important thing, we have to be working with 32-bit float textures when we're doing this kind of stuff, so that it's allowing us to store values that are greater than 1 and less than 0, so we can actually store world space positions in this way. And then, final bit, we just use this, we have a very small box of a scale of 0.1, and we plug that into a piece of geometry, and we use instancing to pull out and use the RGB values from the output of our compute shader to position these things in 3D space. And we have something that is very hard to control. There we go. Yeah, camera control in this guy is a bit of a pain in the neck. There we go. And we have this kind of nice sort of LiDAR effect of this whole thing. And obviously you can go back and change the position, change the size of that. Ooh. And it's all updating nicely. By show of hands, is this technique sort of vaguely familiar to a few people? Okay, about half the room. Okay, that's good. Good to know. But then this is fairly static and boring as it is. So what can we do that is like a development on from that? Actually, first, what I'm going to show you is, again, in the spirit of you do a thing, you think, hey, I found this trick that works for me. What do you guys think? I wrote this article, put it out, and my friend Mickey van Ulst, who I think has spoken at one of these events before, he was like, oh yeah, by the way, you can do this much more easily and completely skip the compute shader bit, which is where we start with the same 3D objects and render it with the same geometry, but we use a feature of the Phong shader, which is the additional color buffer. So what this does is that when the render top performs the render, it makes available kind of like AOVs is how I sort of interpret it. AOVs, if anyone's done any work with kind of like high-end like offline renderers, you can get it to output a whole bunch of things like world space normal, camera space normal, point color. You can kind of get the details of what was actually being rendered at that time and include that in not the final image, but as layers to the final render. And the way we get at those layers is through a render select top. So the one we're really interested in here is the world space position, which is basically outputting in the final render the world space position. So doing all of that matrix math, it's doing all of that for us as part of the rendering process. So this is really nice, and this is like much faster. So now instead of the compute shader, all we need to use is a noise lookup, the same as before, but then we're using that to remap into this. So we're basically just reshuffling the pixels of this render select top. And then the same as before, we're using that to instance a very small box into the geometry. So this is an alternative technique where we're using this color buffer mechanism to get the world space position and then allow us to scatter particles on the surface. And that's all very well and good, but it doesn't allow us to. One thing that's nice about the compute shader approach is we can then incorporate things like lifetime. We can start to add more interesting logic. We can start to add noise to our particles. Which we could still do once we have this. So if we have this remap thing and I start to, maybe add a very, very small amount of noise. So I'm adding a noise into the input of this. Just do input plus noise. And I turn this down to like 0.000. Ooh, that's maybe a little bit. I haven't tried this before, so this is going to be very interesting. Yeah. Let's see. So now I'm going to drag that into there. And now I don't know if you can see on the projection, it's got like a little bit of movement. If I take off that, a little bit more movement. So we can start to, yeah, there we go. Now we're starting to kind of affect our output in that way. But we're going to stick to the compute shader version. And this, again, I'm going to skip fairly quickly through this because I'm conscious of time. So we did have that alternative way of getting the world space positions from our simple 3D scene. But we're going to stick with the compute shader version for reasons that I'm going to show you in a second. So we've got the simple 3D scene, and then that gets plugged into, that's being rendered here. So here we're going back to the previous method where we just have the render, the normal render top, and the depth top that is just extracting the depth information from the scene. And we have a light in the scene as well. And this is, yeah, we're not using the this color buffer feature. But now our compute shader has got a little bit more developed. And I think this is exactly what it was Richard, right, who was talking about in the POPs presentation at the beginning. This is why when you're doing things the compute shader way or the hard way, I'm imagining this is exactly the problem that POPs is trying to solve. So I have this in my first output, these are my world space positions of my particles. But say I want to also maintain a separate texture or block of data that is my lifetime. So I spawn a particle in a particular position, maybe the camera moves. I want to give that particle like a little bit of actual literal lifetime for it to stay in that one position and then disappear and then be reborn over some time. So I get this kind of persistence of vision type effect. But as soon as you start to storing these extra bits of data, you're storing it in textures, and you still have to remember, okay, like the red channel of that texture is my lifetime, the blue channel of this texture is my scale, the green channel is my other thing. Wouldn't it be great if there was a system where you could just name those things and it actually would appear? But this is doing things the hard way. So we are here we have, for those of you that want to get into the compute shader, we are doing the same thing as before, where we are sampling the noise from before. So we're getting a random place to look up into the depth map. Then we're also sampling the lifetime. So we're sampling the outputs, which is it's a handy thing that compute shaders can do that's a little bit more tricky to do with fragment shaders. So it's sampling the output that is also going to write to later on and say, what is the lifetime of this particle currently? So here we are checking if the lifetime is greater than 0. If not, just reduce it by some amount. And also we add a little bit of noise to this amount so that they don't all die at the same time. But if the particle has gone, the lifetime has gone below 0, we consider the particle dead, and we reconstruct a new world position based on the sampling from the depth field. And this is getting us something that starting to look a little bit more interesting. So if I reduce the amount by which I reduce the lifetime every frame, now we're sort of almost getting this kind of ghostly kind of effect on our output, because the individual particles, because our camera position is now moving, the depth field is now moving, we're getting, there's more, each particle is kind of holding the frame. It's almost like a particle feedback sort of effect by getting them to remain in place for longer over more time. So that's one step further of how we can make this a little bit more interesting, especially if we have like some moving content. The next thing we're going to look at is adding color. So that's the example there. Again, we've got exactly the same setup, same 3D scene, same rendering, just the render top and then the depth map. And I was playing around here, so I'm just going to get rid of that. And here, in addition to reducing the lifetime, we're also reducing the position in Y. So now we're starting to get this kind of falling like sand kind of effect, which could be kind of nice. And then we've also adapted this second part of the compute shader where we are sampling the color from the original render. So if I play with the light here, it's going to affect both the render and our particle image. So if I start moving this around, change the light to kind of red, yeah. Okay, we'll just change the dimmer up and down. So you see that's having an effect on our final render, because it's pulling the color data, which is already had lights and shadows applied, into the position that the colors of the particles that's already been created. And then also another thing we can be doing is relighting the particles again. So this is a lighting that is applied to the particles after we've created them or we've added them in world space. So we can be taking this one and making these all like a very bizarre color that has nothing to do with the original scene that we were lighting from. So that's color and movement. But actually, yeah, let's look back at this 1 second. So if I have the depth, this depth scene, this depth render. This is just a top. So what is there that we can do to make this more interesting and affect it even before it goes into the compute shader? Well, we can stick it through a noise, and now our final output is starting to look a little bit more interesting. So we're not applying noise to the particles exactly, we're applying noise to the depth, the depth map. And that can conceptually unlock a whole bunch of other, like, art directable options for you to say, okay, we want this particle system, but we want to be, I don't know, changing the contrast or the distance between the light and dark, or, like I say, applying like a displacement kind of effect to it. But then, in my mind, as I was developing this for a music video, I was like, well, okay, well, this is just a texture. Do I actually need any of this stuff? And which then takes us on to the last part, which is where we've deleted the 3D scene and the render part and the depth map, and we're now into taking just straight up black and white images, say a noise field or a rectangle. So where's the rectangle? There's a rectangle, and plug that rectangle directly into the compute shader, because we're just saying, okay, that's the depth map that the camera saw. Honest, like it's, and you can end up with very demo scene-y, kind of like endless tunnels. And the other important thing that I'm doing here is I've added to the compute shader the world space transform of the camera, because the camera is now actually moving through space. So what we're getting the system to pretend is that we had a camera and it saw, for whatever reason, it saw just kind of like a white rectangle, and it was moving through space like this. So every frame it's adding particles that have this square kind of look, and it's also giving a bit of rotation, so that it's sort of sweeping out in a way these particles as they move through. And then we have different options such as so I'm just switching between the different some different approaches to this. So I'm taking this rectangle, I'm putting it through a displacement field, and using that as the depth field. And then we get into these really interesting tunnels. And then the next step is to sort of work a little bit on the lighting and the rendering, and finally what you may end up with is something that may look a little bit like this, which is the music video I made for an artist called Dustin O'Halloran. And this is exactly this. It's just with a little bit more interesting texture maps applied to the particles, a little bit more creative lighting. There's also, this is another thing. You can also add like a very pixelated noise to the as the depth map. So you now get this kind of like weird floating, like flying through sort of weird cuboid landscapes. And the other thing you can do is render. Here I'm detaching the camera that renders the particles from the camera that produced the depth scene. So if the camera is flying like this, the camera that's producing the depth scene is moving like this. The camera that I'm using to render the particles is slightly detached and is moving around. So the particles are being swept, say, purely on the z-axis, but my camera that's actually rendering the particles is moving around in a bit more of a sort of interesting, kind of chaotic way. So you're sort of getting a different perspective on this whole scene. And I think that's it. That's what I wanted to talk to you about. So thanks very much.
Thanks so much, Owen. Thanks for making the trip down. And I really want to know more about the small Iceland community and how to expand it.
Working on it. Yeah.
Questions? So this character in the back that's about to ask a question is also one of the really, really long-term TouchDesigner users back from Australia.
Yeah, I'm one of the fossils. That looks awesome, man.
Thank you.
Can you maybe talk a little bit about your process in terms of, did you have a vision for this, or is it kind of like an exploration?
It's a bit of exploration. So this one actually this particular video started with playing around with my Kinect camera. So this first bit at the beginning, you can maybe see a hand in there. I was getting my scarf and just like wobbling it in front of the Kinect camera. I was like, oh, that'll do. That's the intro to the video. And then it sort of emerges into something that's a little bit more structured, like, here later, oh, that's still the same thing. So then sort of emerging structure coming from this. There was like a narrative, because the piece itself by Dustin was anxieties around an AI-flavored future. So it was like, oh, you just kind of like that XKCD cartoon of the person like just stirring the pile of data. And it should be like, that's how neural networks work, and you keep on stirring it until something goes better. So that was the initial concept. And then just experimentation and rendering things out. So the whole piece wasn't in any way sequenced within TouchDesigner. It was just kind of like, that is a good look. That's some good material. I'm going to render that out, import it into DaVinci Resolve, and then edited it to the actual to the video. But it comes from a lot of I've been using this system live, so there I'm in control of everything. So the flowers example, this one, this is something that I am using live, and so I have a few things that normally would be controlled by a MIDI controller, like this bump is just is randomizing the seed of the flowers. And then just like a glitter thing, changing the particle size. What else have we got? Some other bits and pieces that would normally be controllable on a MIDI controller. So it came from VJing material first, and then there was an opportunity to make this music video out of it, and that's that.
Well, I'm walking over. So when you perform live, what's that scene like in Iceland if there's only 4 TouchDesigner people?
It's that pretty much. We're 400,000 people just underneath, and a lot of musicians, but not so many places to perform with a complete audio-visual show. So the whole scene is very much kind of in its infancy, and which is very exciting. But I'm also teaching TouchDesigner to graphic design students, which is an interesting challenge, trying to get them to kind of incorporate more procedural thinking into their workflow. Some of them take it, some of them don't. So making new TouchDesigners as much as we can.
Hi. Sorry, I wanted just to say something. By the way, nice talk, and also interesting that you could come up with such nice videos with a few simple tricks.
Thank
I
you.
want to tell you that what you were saying about, how to essentially reconstruct the position and the compute shader version versus. So you essentially, I don't know if, but essentially you rediscovered the first shading, so the first shading pipeline, like if you want to look it up, and maybe, expand and find more tricks.
Yeah.
And interestingly, the thing where you said, oh, then a friend told me, oh, if I write out a separate render target, it's quicker. Not probably now, yes, on all platforms, but it used to be not necessarily quicker actually, because you would write out more data, right? Which instead with the compute part, you compute on the fly on the compute shader.
Yeah.
So, for example, on mobile, used to be not faster, and your way would be faster. But yeah, I think that the first shading thing, if you want to look it up, you will find more ideas. And but yeah, it's nice. The last thing is, by the way, when you do a lot of texture lookups on compute, which is fine because you fetch.
Yeah.
But I think one thing I've seen people forgetting is that on compute, you don't have access to texture filtering because you don't have the derivatives. So sometimes you want to do,
Yes.
trilinear filtering or this stuff that sometimes you might want to do, you won't be able to. So that's another thing to look after. But yeah,
I'm
quite
going to
cool.
need to diagram that. Can you find me later and we'll just draw it?
Yeah,
on a piece of
yeah.
paper?
Okay. Well, that's fine. Cool.
Anybody else?
Hello. It's absolutely sick, by the way. It kind of reminds me of like some kind of LiDAR stuff that you'd see on some, satellite imagery or something. But I wanted to ask, when you were sort of creating the almost lifetime of it, did you ever consider, or did you actually make some kind of LiDAR-ish technologies where you have let's say the 3D models here or the point clouds, which you can sort of scan, and then they reveal themselves as you sort of scan them, maybe as you scan the environment?
Yeah, I mean, that would be interesting to take, because the one thing that I haven't really played with is that this, let's take this one. No, this one's more interesting. So this noise, let's say if I put a channel, I think channel mix on this. No, wait, hang on. If I was to limit the green channel, because the green channel is the Y, so like how much of the image is the Y are we looking at? You could potentially limit that to say like, okay, I'm only going to sample the bottom quarter of the image and then like increase that, or like have like a band moving up and down. Yeah, that's a really good idea, and that would live within this kind of sample, this texture that you're using to sample the depth image. Yeah, for sure. Or put into the compute shader just like a limit, just saying like if the Y is above this or below this, you just kill it, set the lifetime to 0, and then it'll get recycled. Yeah.
Sweet. Thanks, man.
Thanks.